Alrighty guys, let's go ahead and finish these notes. Just get them out of the way. We're going to finish unit, I should say, 2.4. And today there's nothing groundbreaking at all. It's just more of what we were talking about yesterday. The only difference is more transformations, but that's it. So a little bit more manipulating just because, but no new knowledge, which is really good news for a lot of people. We're going to graph 1 over 3 to the x. This is going to be exponential decay. We recognize it as decay because the base is between 0 and 1. So we know it goes wee like that, and it approaches the x-axis because there is no vertical shifting. So it's just a b to the x, which means it automatically goes through 0, 1, like yesterday's b to the x's did. And because it's exponential decay, and I know it's going to be going up as it goes to the left, I'm going to use negative numbers for x to evaluate first because those will be easier. So x equals -1. 1/3 to the -1, that's 3, because remember, negative exponents just flip things over. 1/3 to the -2, that's 3 to the 2, which is 9. And then after that, the numbers get way too large. They don't even fit on the grid. I can go to the right. 1/3 to the first is a 1. Wow. Okay, so those numbers got really small really fast. Then it goes 1/9, 1/27. I mean, really small, really fast. So I'm just going to do that. And let's see if I can. Okay. But if I'm pulling the pin towards me, I can't predict how curved it needs to be to get through those, which is why it's easier to go like that. Move the page. Anyway, no, I'm good. Thank you, though. Now we are going to graph this one. What I don't want to do is I don't want to have to plug in values for x and subtract 4 and then rate. Now, I don't want to do any of that. Instead, what I want to do is understand transformations and go ahead and fill in part B right now. Get out of here, pencil. I'm going to fill in part B right now. I'm going to describe the transformations for g of x. Right 4 units, up 2 units. That, I'm not sure what just happened. I had a stroke. So I'm going to shift it right 4 and up 2. So this dot, no, I need the green. This dot, right 4, 1, 2, 3, 4, up 2, 1, 2. This dot, right 4, 1, 2, 3, 4, up 2. This dot, right 4, 1, 2, 3, 4, up 2. Oh, I'm off the grid. It's way up here. You know what else shifts up 2? The horizontal asymptote. So it's going to go from x equals 0 to x equals 2. It says find the y-intercept. Well, we can't even see it. It's way up here somewhere. So how are we going to find it? Plug in 0 for x. That'll do it. One-third to the -4 is the same thing as saying 3 to the +4, which is 81. And 81 plus 2 is 83. There you go. We found it. Easy enough. Oh, God. You guys are always on your phones back there. You're always on your phones or on your calculators or doing your homework or talking about Fortnite. The four of you are always not doing what I'm doing. All right, anyway. This function's got a lot going on. We cannot describe it as an exponential growth or decay function. The reason why is because a is not positive, so it's just some exponential function. That doesn't mean we can't graph it. We can still graph it. We just need to figure out where it lies. Well, I mean, how about we just start with easy x's to plug in? X equals 0 is always going to be really easy to work with. It's going to do nice things when you don't have any horizontal shifting. The reason why is because every base to the 0 power equals 1. So if I use x equals 0, I get 1 times negative 1/2, which is going to give me negative 1/2. How about x equals 1? Well, if you say x equals 1, you just can ignore the exponent. Negative 1/2 times 1/2 is negative 1/4. Oh, it got really small. Since there's no vertical shifting, I know that the x-axis, y equals 0, is still the horizontal asymptote. It's negative 1/4, yes. Did she say y? Okay. Now, let me go to the left. Because I already know as I go to the right, I'm just going to get really close to this horizontal asymptote. Let me go left. Use negative 1. Remember, when you raise a fraction to a negative exponent, it flips the fraction over and makes the exponent positive. So to say 1/2 to the negative 1 is actually going to give me a 2. So I can just say negative 1/2 of 2. Negative 1. We can apply the same logic if x is negative 2. 1/2 to the negative 2 is 2 to the 2, 4. But negative 1/2 of 4, negative 2. Use negative 3. 1/2 to the negative 3 is 2 to the 3rd, 8. Negative 1/2 of 8. And then, yep. And then use negative 4. That's 2 to the 4th. Negative 1/2 of 16. Like this. So yeah, we've got this curve going on like that. And getting really close to the asymptote there. So how does that compare to that function? The easiest way to answer that question is to try to write y as a base 2 equation. Because if you have the same bases, then we can easily describe all of the transformations. I've kind of already told you how to do that. Negative exponents flip fractions over. And now you can see the 3 transformations that must be done to 2 to the x to get here. And it is 3 because every negative sign, every negative multiplication is a reflection. And then that 1/2 on the front is just a vertical dilation. So I'm going to reflect over the x-axis. I'm going to perform a vertical dilation, factor 1/2. Yes, Adi? Okay. Oops. And lastly, reflect over y-axis. All right, Adi, what's up?
You can also say that it's shifted directly.
No, in order for it to be... Oh, I see what you're saying. You're saying if I had manipulated this number, we could do that also. alternate version of the equation, recognizing that 2 is also, or 1/2 is another power of 2, right? We could have written it like, let's see, where do I have room? You know, I don't really have room on the paper, so I'm just going to grab a piece of scrap and write on that. And we could have done that from the beginning. We could have said negative 1/2 to the x. We could have said that this was negative 1 times 1/2 to the 1 times 1/2 to the x, which would be negative 1/2 to the x plus 1, which is negative 2 to the negative 1 to the x plus 1. So negative 2 to the negative x minus 1. But it's not about the difficulty of it, it's about the fact that you can manipulate it. So what does this say? This says shift right 1, reflect over y-axis, reflect over x-axis.
That's what I did. I just like,
And that's not wrong. That's also correct. You can do that as well.
I was just thinking of it as like the normal function.
Mhm.
How I see it.
You were trying to get it so that it was just base 2 with no vertical dilations. So for exponentials, all horizontal shifts can be written as vertical dilations, and vice versa. All vertical dilations can be written as horizontal shifts of some sort. That doesn't mean they're always pretty, though. But because these were both actually base 2 numbers, we were able to do it pretty. Yeah.
Logarithmics are like opposite.
Logarithmics behave exactly the opposite way, yes.
We have opposite or horizontal dilation.
Horizontal dilations are vertical shifts, yes. Which we'll do when we get to logarithms later in the lessons. But yep. The reason why is because they're inverse functions. Okay. All right. Last 4 examples. We have this function, and we're asking what would this do to it. That would shift right 3. That would give me 4 to the x minus 3, which is shift right 3 units. But that's not the only correct answer. The other correct answer is a little bit more ridiculous. Remember, all horizontal shifts for exponentials can be described as a vertical dilation. Because 4 to the negative 1/3 is 1 over 4 to the third, or 1 over 64. So we could have just said vertical dilation, factor 1 over 64. Would I have done that? No, I wouldn't. But I'm just saying it can be done. You never know when I might say, describe this using horizontal transformations only as a test question. And then you go, oh, that's a base 4 number. So I can convert it to this and describe it as a shift right 3 units. See, that demonstrates understanding of how these things can be manipulated. This one is much easier because it only has one answer. Shift up 5. Shift up 5 units. Ta-da! That's it. Now this one, this says replace your x with a negative 2x. As far as describing the transformations are concerned, there's only one way to describe these transformations. There are alternate versions of the equation, but there's not alternate descriptions of the transformations. What I have here is reflecting over the y-axis, horizontal dilation, factor 1/2. Like I said, we could manipulate the equation, though. If we wanted to, we could say, and we don't have to, we could have done this. And 4 to the negative 2 is 1 over 16. So it's an alternate version of the equation, but the transformations stay the same. So it's just, again, beneficial to be able to manipulate them and see what you can do with it. Completely up to you, though. And this last one. Whoa. Dropping F-bombs. Put a negative 3 on the front. Replace the x with an x plus 1. Strap a minus 2 to the end of it. There it is. Now you have 3 different vertical transformations. You must be careful. When you describe vertical transformations, more than one of them, you need to follow PEMDAS because vertical transformations perform actions in the way that we think they would, which means follow the order of operations. So the 2 multiplications, their order doesn't matter because they're both multiplication, but the shift down to needs to be said after the multiplications. So let's go, the first negative is reflect over x-axis. Then we have vertical dilation, factor 3. Then we have shift down 2. Lastly, the horizontal translation, which could be rewritten and described as a vertical dilation. But for now, let's just describe what happens when we have x plus 1. Shift left 1 unit. I wrote units, 1 units. Just for poos and giggles, realize that this says 4 to the x times 4. So I can manipulate this. Four times 3 is 12. Because if you do it this way, there's only 3 transformations to describe instead of 4. Would I try to graph this? No, I wouldn't. This would be easier to graph because I could tell myself exactly what to do with my coordinates. Oh, just shift them left 1. This one's going to go to all kinds of wacky places. But again, at least you'd have the ability to describe it in a separate way. You could say, reflect over x-axis, vertical dilation factor 12, shift down 2 units. It's a little bit less work to describe. I think it's more work to actually graph. What do we think? We're okay with this stuff? You know why? Because you're nerds.